Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Last lesson, you learned how Docker lets you package an application into a container and run it on a single server. That's perfect, until your application becomes popular. Imagine your website suddenly goes viral. One container becomes 10, then 100. Now imagine one of the servers crashes at 3 a.m. Who's restarting all those containers? Who's deciding where they should run? Who's making sure customers never notice? That's exactly the problem Kubernetes was built to solve. Instead of managing containers one by one, Kubernetes manages your entire application automatically, keeping it running, scaling it when traffic increases, and recovering from failures before most users ever notice. Think of Kubernetes as the operating system for your data center. Just like Windows manages applications on your laptop, Kubernetes manages containers across an entire cluster of servers. You tell Kubernetes your desired outcome. For example, I want 3 copies of my web application. Kubernetes figures out which servers should run them, how to distribute them, how to recover if one crashes, how to scale when traffic grows. Originally developed at Google and now maintained by the Cloud Native Computing Foundation, Kubernetes has become the industry standard for container orchestration. The smallest thing Kubernetes deploys isn't actually a container. It's a pod, a small wrapper that contains one or more containers sharing the same networking and storage. That's the first building block we'll explore. Before we dive deeper, here's the entire Kubernetes story in less than a minute. A developer builds a container image. Kubernetes receives a deployment request. The control plane decides where the application should run. Worker nodes start the pods. Services provide stable networking. Controllers continuously monitor everything. If a container crashes, Kubernetes replaces it. If traffic doubles, Kubernetes can launch more pods. If a server fails, applications automatically move to healthy machines. Everything we'll learn today is simply a deeper look at one of those steps. Without Kubernetes, you start each container by hand, pray nothing fails, and if a server dies, you're down until someone wakes up. With Kubernetes, you describe the desired state. I want 3 copies of this app, and the system constantly works to make that true. If a node crashes, replacement pods appear on healthy machines automatically. Same application code, completely different reliability. That's the difference orchestration makes. Let's make sure that's stuck. Let's lock this in. Think about what you'd do if you had to run 10 containers across 5 servers manually, restarting crashed ones and juggling ports. What does Kubernetes automate that saves you from that nightmare? Before we start deploying applications, let's meet the brains of the cluster. Every Kubernetes cluster has a control plane. Think of it as mission control. Whenever you create, update, or delete something, your request passes through 4 major components. The API server is the front door. Almost every command goes through it. The scheduler decides which worker node should run each new pod. The controller manager constantly compares what's actually running with what you asked for, and fixes anything that's drifted away from the desired state. Finally, etcd stores the cluster's entire configuration. If the API server is the brain, etcd is the memory. Together, these components continuously work to keep your cluster healthy, even when hardware or applications fail. Time for a quick recall checkpoint. Think about the architecture you just saw and reach back to our earlier lesson on IaaS. A pod is the smallest thing you'll ever deploy in Kubernetes, and it's not a container. It's a thin wrapper that can hold one or more tightly coupled containers. Pods share network and storage, so containers inside the same pod can communicate via localhost and share volumes for data exchange. Most pods you'll create will hold just one container, like an Nginx web server. But the design is flexible enough to put two containers side by side when they really need to live on the same machine. The kubectl, an agent on each node, ensures that the containers defined in a pod are running and healthy. And when you're ready to deploy, you'll interact with the cluster using kubectl, the Kubernetes command line tool. This tiny file is a pod manifest. You write what you want, a pod named Nginx pod with one container running nginx.latest, and hand it to the API server. The scheduler finds a healthy node, and the kubectl on that node starts the container. Run kubectl apply with the file. Then kubectl get pods. A single command, and you've deployed your first Kubernetes pod. Imagine a web server and a log forwarding agent sharing the same pod. The web server writes access logs to a shared volume mounted in both containers. The sidecar container reads those logs from the same volume and ships them to a central log store. Because they're in the same pod, they share the same network namespace and can easily communicate through the file system via that volume. No heavy networking, no separate services. This is the sidecar pattern, and it's one reason Kubernetes pods are more than just a single container. The number one mistake beginners make with deployments? Thinking it's just a pod runner. In reality, it's the control center for your whole application's health. And missing that fact breaks production rollouts. A deployment is the object you'll interact with most. You tell it, I want 3 replicas of this pod template, keep them running, and when I change the template, roll it out without downtime. Under the hood, the deployment creates a replica set that maintains the specified number of pod replicas. If a pod dies, a new one appears. Deployments give you declarative scaling, rolling updates, and one-command rollbacks. This YAML declares a deployment that wants 3 replicas. The selector matches pods with the label app, my app. The template section defines exactly what those pods look like. When you apply this manifest, Kubernetes creates a replica set, which then starts 3 identical pods. Run kubectl get pods, and you'll see them appear, all from a single file. Quick checkpoint. You just learned about deployments and scaling. Let's see if you caught the key detail. Here's one of the first surprises new Kubernetes users encounter. Pods are temporary. If a pod crashes, Kubernetes creates a replacement. But that replacement usually receives a different IP address. Imagine telling thousands of customers, our website moved to a new IP. Obviously, that's impossible. That's why Kubernetes uses services. A service provides one permanent address while quietly directing traffic to whichever healthy pods are currently running. Users never know a pod was replaced. Applications never need to memorize pod IP addresses. The service becomes the stable front door for an ever-changing group of pods. That's one of the reasons Kubernetes can recover from failures so gracefully. The number one mistake beginners make: exposing everything as node port and then asking why the cluster is full of open holes. When you create a service, you have several types. Cluster IP keeps things internal, only reachable within the cluster. Node port punches a static port on every node, so you can reach the service via any node's IP and that port. Load balancer goes further. It asks your cloud provider to provision an external load balancer with a public IP, perfect for user-facing apps. There are also external name and headless services for specific use cases, but the three you'll use most are cluster IP, node port, and load balancer. Let's test what you just learned about services and compute models. Imagine a naming conflict wiping out the wrong deployment across teams. Without namespaces, that's a real risk. Namespaces split one physical cluster into multiple virtual clusters. You can have a deployment called web in both dev and prod without conflict. You can also set resource quotas to limit CPU and memory per namespace, and use role-based access controls to restrict permissions within each namespace. These are optional but powerful. Namespaces are your first line of defense in multi-team clusters. First, let's see what namespaces already exist. Run kubectl get namespaces. You'll see default, kubesystem, maybe others. Now create a new namespace called staging, just a logical partition. Then spin up an nginx pod inside that staging namespace using kubectl run with the namespace flag. When you run kubectl get pods with the namespace flag, you only see staging's pod. No clutter from other teams' resources. Namespaces give each team their own view of the cluster, preventing resource name conflicts and allowing you to set resource limits and permissions per team. They don't provide full network isolation by default, but they're a key building block for multi-tenancy. And when you later need persistent storage, Kubernetes provides persistent volume claims, a request that binds a pod to a disk so data outlives the pod. Here's how all the pieces fit together. A real Kubernetes application in the production namespace. A user hits the load balancer service, which spreads traffic across multiple front-end pods. The front-end talks to the back-end API through a cluster IP service. It uses the service's internal DNS name, never a pod IP. The backend pods can connect to a database that uses a persistent volume claim for durable storage, so data survives pod restarts. Every piece declares its desired state, and Kubernetes keeps it running. That's a complete stack, owned by a namespace. No confusion, no collision. The single biggest configuration mistake in Kubernetes? Hard-coding credentials or database URLs in your container image. That bakes sensitive data into layers and forces a full rebuild whenever a setting changes. Kubernetes provides ConfigMaps for non-sensitive configuration and secrets for sensitive data like passwords. Both can be injected as environment variables or mounted as files, so your image stays the same from dev to prod, and only the config changes. For example, a config map might store the database connection string as an environment variable. Update the config map, restart the pod, and the new setting takes effect without rebuilding the image. Creating a secret is one command. Kubectl create secret generic DB pass, passing the literal password. Then in your deployment YAML, you reference that secret. Kubernetes makes the value available to your container as an environment variable. So your code reads DB password like any other env var, but the password never lives inside the image. Rotating it just means recreating the secret and restarting the pods. No rebuild, no new image. Before we move on, a quick recall drill. First, configuration. Why avoid baking passwords into container images? And which Kubernetes resource solves this? And from our earlier series, when you launch a virtual machine using IaaS, which 3 layers do you, the customer, still have to manage yourself? Pause and answer, then check. Imagine a worker node fails. Hardware crash, 3 pods gone. A human admin would need a page, then scramble to restart them manually. In Kubernetes, the control plane continuously reconciles actual state with your desired state. It detects the lost pods and automatically schedules replacements on healthy nodes, bringing the replica count back without manual intervention. That reconciliation loop, where Kubernetes constantly works to match reality to your YAML, is the engine behind self-healing, scaling, and rolling updates. When you update your deployment image, Kubernetes performs a rolling update. It doesn't kill all old pods at once. It creates new pods gradually, verifies they're healthy, then replaces the old ones. Throughout the process, the service continues routing traffic to healthy pods, so your users never see an error. If the new pods crash, Kubernetes can automatically roll back, eliminating outages. You might be wondering, do I really need Kubernetes? If you're deploying a single personal website, probably not. But once applications grow into dozens or hundreds of containers running across multiple servers, manual management simply doesn't scale. That's why organizations around the world adopted Kubernetes. Not because it's trendy, because it solves real operational problems. Today, Kubernetes powers everything from startups to many of the world's largest technology companies. And the best part? You don't need a giant data center to start learning. You can build real Kubernetes skills on a laptop using tools like Minikube or Kind, then apply those same concepts to cloud platforms like Azure Kubernetes Service, Amazon EKS, or Google Kubernetes Engine. The tools may change. The Kubernetes concepts stay the same. Let's do a quick recall drill. When a pod crashes in a deployment, what Kubernetes mechanism automatically replaces it? And why must you avoid hard-coding configuration inside a container image? Pause, then I'll reveal the answer. The Kubernetes community recognizes 3 main certifications: CKA for administrators, CKAD for application developers, and CKS for security specialists. These exams are performance-based. You work on live clusters, not multiple-choice questions. Always check the official certification sites for the current exam domains and pricing. If you're planning to pursue one, spend 20 minutes today reviewing the exam curriculum. It's the best roadmap for what to study. You can set up a full Kubernetes environment on your own machine for free, using open-source tools or browser-based labs that require no installation. Interactive web scenarios let you practice hands-on tasks with zero local setup, and guided training platforms offer pre-configured clusters with step-by-step walkthroughs. Spend 20 minutes a day in any of these, and you'll build real muscle memory fast. So let's lock in the 3 big takeaways. Kubernetes automates the full container lifecycle. You declare the desired state, and it continuously works to keep your app running. The core objects are pods, deployments, and services. Once you're solid on those, you can deploy almost anything. And you've just seen how fast you can spin up a working cluster with Minikube and kubectl. The barrier isn't technical, it's just starting. Next in the IT Fundamentals Masterclass, Serverless Computing. You'll deploy code without ever touching a server. Subscribe and hit the bell so you don't miss it. If Kubernetes changed how you think about infrastructure, wait until you see what zero-server architecture really looks like. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.